We want to solve this system of equations. So first note that this is a system of nonlinear equations. So we'd like to begin by classifying what each curve is, so we can kind of visualize how many intersections we might potentially end up having. So let's start with the first curve. So looking at the coefficient of the x squared term and the y squared term, we'll notice that the first coefficient is a positive 1, and the coefficient of the y squared term is a negative 3. So because we have those opposite signs, one positive and one negative, we have a hyperbola for our first curve. So first curve here is a hyperbola. Now we look at the second curve. Both x and y are squared again, and again looking at the coefficients of a positive 2 and a negative 7, we have one positive, one negative, therefore we have another hyperbola. So essentially we're looking at the intersection of two hyperbolas. So if you were to check this system graphically, we could solve both of these equations for y, and then we could utilize our calculator. We could actually graph both hyperbolas, but it would require us to use the y1, y2, y3, and y4. We'd have to use actually 4 because we'd be entering, remember, a positive square root as well as a negative square root for each one. So I encourage you to check your answers graphically using your calculator, but we'll work on solving this one algebraically right now. So this system is set up nicely for elimination because we have all the variables on one side and both the x values are squared and the y values are squared. So I'm going to go ahead and work to eliminate the x squared terms. So I'm going to essentially multiply my top equation by negative 2. So I'm going to be multiplying the left-hand side as well as the right-hand side of my top equation by negative 2, so that I will be able to eliminate the x squared terms. So my new top equation will be negative 2x squared plus 6y squared is equal to negative, that would be a positive, is equal to positive 2. My second equation I haven't altered, so 2x squared minus 7y squared is equal to negative 5. And now I'm ready for my elimination. So in adding these two equations together, this is called your elimination method, also called the addition method if you prefer. We notice negative 2x squared plus 2x squared is equal to 0. Then we end up with a negative y squared is equal to negative 3. So solving for y squared is equal to positive 3. So y is going to equal both the positive and negative square root of 3. So at this point, I like to go ahead and set up my ordered pairs because remember, we're searching for the intersections of the curves. So right now it appears that we have possibly two intersections, one with a positive square root of 3 for the y value and another one with a negative square root of 3 for the y value. So now that we have our y value, we'll do substitution, sometimes called back substitution, into the original, one of the original two curves to solve for the x value. So I'm going to go ahead and take this back into the first curve and do my substitution. So my first curve, which was x squared minus 3y squared, I'll leave that blank for now, because now I'm going to go ahead and substitute in my first y value, which was the square root of 3, and I'll solve for x. So I would end up here with x squared. The square root of 3 squared is 3, times 3 would be a minus 9, is equal to negative 1. So I'll go to the right here. It looks like x squared is equal to 8. Therefore, x is equal to plus or minus the square root of 8, which would simplify to 2 times the square root of 2, both the positive and the negative. So notice again, this was when I inputted right here, I was inputting the square root of 3. Let's see if I can circle that better for you. Here I was inputting the square root of 3. That was my y value, and I obtained two x values. So that means that I can have 2 times the square root of 2 as my x value when y is the square root of 3, but I'm also gaining another intersection when y is the square root of 3, I'm also gaining negative 2 square root of 2 for my x value. Now we need to do substitution again, this time with the negative square root of 3. But notice, if I just come down here in my work, and if I add my negative here, so now I'm inputting a negative square root of 3 for the y value, the algebra is not going to change because I'm squaring this quantity, so I would still be getting 9. In other words, I would obtain these same exact x values, both positive and negative 2 rad 2, when the y value is negative 3. So that means I have positive 2 rad 2 for the x value when x is equal to 2 rad 2, y is negative rad 3, but in addition, x is equal to negative 2 rad 2 when the y value was negative rad 3. So I really end up with a total of 4 intersections. Once again, I would encourage you then to go ahead and try it on your calculator. So let me take you through the process of how to check it on your graphing calculator. So looking back at the original system here, we would go ahead and need to take my top curve, my top hyperbola, and I'll go ahead and solve for y. So let's kind of go through these steps with you so you can check some of your answers using your graphing calculator. So I would subtract the x squared from both sides. I would divide by negative 3. So that would be negative 1 minus x squared all divided by negative 3. And then I will square root both sides. So I end up with positive and negative square root of negative 1 minus x squared all divided by negative 3. So really what I will be doing here, I'll be entering the positive square root on my calculator in my y1, and then I'll enter the negative square root in my calculator in my y2. So that negative would then be on the outside. And what this is doing, of course, is basically graphing the top part of the hyperbola and then the bottom part of the hyperbola. Since the hyperbola is not a function, remember, the graphing calculator doesn't handle it well because it's not a function. So it's like we fool the calculator into graphing it for us by graphing the top piece and bottom pieces separately. And then we would need to do the exact same thing for my bottom curve, my bottom hyperbola. So once again, solving for y, we would subtract 2x squared from both sides, divide by negative 7, and then square root both sides. So we would end up with y is equal to both the positive and negative square root of negative 5 minus 2x squared, all divided by negative 7. So we will now utilize my y3 and y4 on my graphing calculator in order to enter this hyperbola. So the positive going in my y sub 3, and then the negative square root can go in the y sub 4. So I encourage you to go ahead and enter in these 4 curves, which will basically give us both of the hyperbolas. Basically, these are the 4 we'd go into our calculator with. And then practice calculating the intersection and verify that we get the same intersections. Remember, of course, going back to the intersections that we have here, these are the exact answers, which the calculator cannot generate for us. So you won't get 2 rad 2. Of course, you'll get the decimal approximation for that. Same thing for the square root of 3. But when you graph it, at least you can visualize that once you get the 4 curves into your graphing calculator, you should be able to visually see that there are 4 intersections for these hyperbolas.